So in this segment, we're going to talk primarily about explaining the factors that result in both endothermic and exothermic solvation energies. So heat of solution, let's talk about the concept of the heat of solution. Obviously, it's an enthalpy, but the enthalpy of what process? That's what you always want to be asking. So when some compounds, such as sodium hydroxide, dissolve in water, a lot of heat ends up being released. It's actually quite surprising when you put this solid in and you dissolve it, you can feel it. You can feel the beaker getting hotter. So in other compounds, such as ammonium nitrate dissolve in water, heat is absorbed from the surroundings. You actually can feel it cooling down. It's an endothermic reaction. So why is this? What are the factors that go into play, whether something is endothermic or exothermic? So what do you have to do to make a solution? To make a solution, you must separate the solute into constituent particles. Therefore, the change in enthalpy of the solute is endothermic. And here we're saying this is the change in enthalpy to separate the solute into essentially a gas phase. You also have to separate the solute molecules from each other. Not completely, right? You're just making room for the solute to be inserted. This is an endothermic process as well. You're breaking bonds. Not really breaking bonds, you're breaking intermolecular interactions. You mix the solute particles and solvent particles together, and that's the next step. Now that is exothermic because now you're gaining interactions. Whenever you bring the molecules into contact, you're lowering the potential energy, you're gaining extra attraction between molecules. These are the attractions between the solutes and the solvents. So the overall change in enthalpy for making a solution depends on the relative sizes for these three processes. So so those are the three processes we consider. It's sort of like the Born-Haber cycle. This is a little bit simpler since we're assuming the molecules stay together. They're not exchanging electrons or anything. We're just looking at which interactions we have to break and which ones we have to form. Okay, so yeah, step one, separating the solute into its constituent particles so it can go into solution and be surrounded by solute. The enthalpy of this is positive. It's an endothermic process. Next, we need to separate the solvent particles sufficiently to make room, separate the solvent particles sufficiently to make room for the solute. So in this case, it's also endothermic. We're breaking interactions. And then we mix them together and we gain interaction energy. So this is an exothermic process. So let's look at the different ways it can combine. Let's say that in this case, you separate the solute particles and you go up in energy. You separate the solvent particles, you go up in energy. Now you've got your solvent separated, your solute separated, and you mix them together and gain all this enthalpy. Now in this case, if the enthalpy you gain from mixing them is bigger than the sum of the two enthalpies you lose, it'll be a net exothermic process. You go lower in potential energy and you release heat. But what could also happen is the enthalpy of separating the solute and separating the solvent gets you to a certain point in high energy, and you don't really gain that much energy back as you don't get that much energy back as the solute and the solvent come together. Your delta H of mixing is not quite as large as the sum of two delta H of separating them. So this would be a net endothermic process, and it would only happen spontaneously if it being driven by entropy.